Section 1 Introduction. We'd like to start by discussing a very pertinent topic in natural language processing, large language models, LLMs, and how they've been causing quite a stir due to their exceptional ability to follow commands. This is evident across various circumstances, whether we're working with 0 prior examples or a handful of them. That said, it's crucial to note that their performance does fluctuate depending on the instructions they're given. Intriguingly, even a simple rephrasing of the original command can affect how well LLMs execute specific tasks. Hence, we're still a bit in the dark as to the specifics of when and how these models can generally adhere to instructions. You see, the ability of LLMs to follow instructions is especially critical when they serve as the bridge between humans and AI models. In this role, humans can guide LLMs to tackle complex tasks through well-defined instructions. But, there's a catch. Crafting these instructions, a process often termed as prompt engineering, heavily depends on human expertise. It involves a tedious and expensive cycle of trial and error. Therefore, a significant challenge we face is figuring out how to automate the search or optimization of instructions for any given task. Now, here's where it gets tricky. Instructions are not simple entities. They're made up of distinct words or sentences, which makes it tough to optimize them in a continuous space. Plus, creating a task-relevant and easily understandable instruction requires dealing with the combinatorial optimization that comes with complex structural constraints. Moreover, the most effective LLMs, for instance, ChatGPT and GPT-4, are pretty much black boxes. Working only with their application programming interfaces, APIs, makes it unviable to create gradient-based instruction optimization, which would necessitate backpropagation through these models. To navigate these obstacles, we're introducing an approach we've dubbed InstructZero. It aims to effectively and efficiently handle the combinatorial optimization of instructions for API LLMs. How does it do that? Well, instead of straight-up optimizing the instruction, InstructZero enhances a soft prompt to an open-source LLM, for example, Llama, Stanford Alpaca, Vicuña. This enhancement allows the LLM to generate an easily understandable and task-specific instruction, given a few examples of the target task. This is all thanks to the LLM's in-context learning capability. The generated instruction is then assessed on the target task by the black box LLM, and its performance guides the soft prompt's optimization to generate even better instructions. We view the soft prompt optimization as a type of Bayesian optimization in a latent space. Here, each soft prompt and the corresponding zero-shot performance become an input-output pair for the optimization objective. To establish a latent space kernel that mirrors the similarities in the instruction space, we create an instruction-coupled kernel that aligns the kernels of both spaces. This alignment facilitates the efficient exploration and exploitation of soft prompts in a low-dimensional latent space, leading to an effective search for the optimal instruction in a textually rich and highly structured space. To put InstructZero to the test, we ran evaluations using a combination of a cutting-edge open-source LLM and a black-box LLM, namely 13B Vicuña and GPT 3.5 Turbo, also known as ChatGPT. The results were very encouraging, demonstrating a significant enhancement in ChatGPT's performance when using the instructions optimized by InstructZero. Impressively, it achieved state-of-the-art results on all 32 tasks from Big Bench. As part of our study, we visualized the optimization process of InstructZero and provided the generated instructions for each step. Compared to non-optimized methods that employ ChatGPT to generate instructions, InstructZero outshines them even when using a much smaller Vicuña model. Section Summary. Large language models, LLMs, have shown remarkable capabilities in following instructions, but their performance is sensitive to the choice of instructions. InstructZero is proposed as an effective and efficient approach to tackle the zeroth-order combinatorial optimization of instructions to API LLMs. It optimizes a soft prompt to an open-source LLM, which can generate a human-readable and task-relevant instruction given a few exemplars of the target task, and then the instruction is suited to the black box LLM for evaluation on the target task, whose performance is used to guide the optimization of the soft prompt toward generating better. Section 2 Instruction Optimization. In this section, we're examining the process of optimizing an instruction, let's call it V, when applied to a language learning model, LLM, that acts as a black box. We'll call this model F. We're aiming to improve how well this model performs with a particular task using an input, X. Our goal is to boost the performance of the output, represented as F, V, X, in relation to an evaluation metric, H, that compares this output to the ground truth, or Y. We're essentially looking to optimize the instruction, V, to reach the highest possible score, H, F, V, X, Y, when an example, x, y, is drawn from the data distribution of the task. However, there are two major challenges with this. 1. It's a complex optimization problem, involving lots of combinations and restrictions. For instance, the instruction v for LLMs like ChatGPT or GPT-4 consists of discrete tokens that need to form human-readable and task-specific sentences. This makes the optimization space large, discrete, and very structured, with many semantic constraints. Unfortunately, we don't have efficient optimization algorithms for this kind of scenario. 2. The optimization has to be done without full knowledge of what's happening inside the LLM. We can only input text and get text output from this black box model, which means we can't use backpropagation or gradient-based algorithms to optimize our instruction. To navigate these issues, we've developed InstructZero. Rather than optimizing the instruction v in its original form, InstructZero applies a soft prompt p to an open-source LLM g. This LLM then converts the soft prompt to a human-readable and task-relevant instruction v using kappa examples drawn from the target task. The instruction is then applied to the black box LLM to give a zero-shot prediction f, v, x. We then collect performance scores from target task data to estimate our objective function, using a method called Bayesian optimization. This helps us suggest new soft prompts for creating improved instructions. InstructZero's process can work with different open-source LLMs, like Llama, Alpaca, and Vicuña, and black box LLMs like ChatGPT, GPT-4, Claude, Palm 2. By using an open-source LLM to create the instruction, InstructZero simplifies the optimization challenge. It converts it into a feasible black box optimization problem within a smaller space, using a technique known as latent space Bayesian optimization. The full procedure is outlined in the algorithm provided. Section Summary. The section discusses the optimization of an instruction versus applied to a black box LLM f, CDOT, to maximize the output f, v, x, s performance h, f, v, x, y. For an example, x, y, drawn from the data distribution d underscore t of task t. However, this optimization is challenging due to the high-dimensional, discrete, and highly structured optimization space v and the black box nature of the LLMF, CDOT. InstructZero addresses this challenge by optimizing a soft prompt p applied to an open-source LLMG, CDOT, to generate a human-readable and task-relevant instruction versus, which is then applied to the black box LLMF, CDOT, to produce zero-shot prediction f, v, x. Section 2.1 From Structured Combinatorial Search to Low-Dimensional Continuous Optimization. We've developed a system we call InstructZero that uses a method known as in-context learning. This system takes advantage of an open-source large language model, abbreviated as LLM. In our system, we generate instructions, denoted as v, by pairing a soft prompt, which is a dimensional vector p, with several input-output examples. These examples come from the task-specific distribution and are represented by their token embeddings. To make the process more manageable, we've reframed the complex combinatorial instruction optimization as a simpler continuous optimization problem. We now maximize the expectation over the input and output pairs coming from our task's distribution. However, v is no longer a fixed instruction but is instead the output of our LLM, which takes p and the input-output examples as its input. While this reframing simplifies the problem, it introduces another challenge. Even though we have transformed the problem into a continuous optimization of a soft prompt p, we still need to solve a black box optimization problem. This is because p, as an input token to an open-source LLM, usually has a very high dimensionality. This dimensionality is often in the thousands, such as with Vicuña, and this is too large for existing black box optimization approaches to handle. To address this, we optimize a lower dimensional vector p instead and project it to a higher dimensional space using a simple random projection. We can then use these projected tokens as inputs to our model. This random projection preserves the distances between points, which ensures the consistency of optimization in both the original and reduced space. Furthermore, because of the in-context learning capability of the open-source LLM, the low-dimensional soft prompt, when combined with the input-output examples, is sufficient to generate a wide range of useful and relevant instructions. Finally, by replacing p with our projected tokens in the equation, we can reduce the instruction optimization problem to maximizing a black box function in a lower dimensional space. This function depends on the expectations over the input and output pairs from the task's distribution, with v now being the output of our LLM, taking the projected tokens and input-output examples as input. Section summary. The paper proposes a method called InstructZero that generates instructions for a black box language model, LLM, using in-context learning. The combinatorial instruction optimization is reframed as a continuous optimization problem, which is reduced to a low-dimensional space using a simple random projection. This allows for the optimization of a black box function in a low-dimensional space, making it feasible for existing black box optimization approaches. Section 3. Bayesian optimization with instruction-coupled kernel. In the previous section, we transformed the task of generating instructions into a black box optimization problem in a low-dimensional space. In simpler terms, we aim to maximize a function h given a parameter vector p in d-dimensional space, which we aim to solve using Bayesian optimization, BO. Bayesian optimization is a method that seeks to estimate the maximum of a black box function. In our case, that function is h, p. The Bayesian optimization algorithm iteratively updates its understanding of h based on newly collected pairs of parameters p and corresponding function values h, p, and keeps searching for new parameter vectors p until it finds the one that yields the highest possible function value h, p. In order to calculate h, p, for a given parameter vector p and its corresponding instruction, we use the average zero-shot performance on a validation dataset. Zero-shot performance refers to how well the model performs on tasks it has not seen during training. For the Bayesian optimization of the soft prompt, we utilized a Gaussian process, GP, as the prior for our black box function h. This GP is defined by a mean function, which is 0 in this case, and a covariance function also known as a kernel function. We maintained a set of soft prompts and their corresponding function values, collected from all previous steps of the optimization. Then, we updated our understanding of the black box function using a Gaussian distribution with a certain mean and variance. These functions are derived from the previously collected soft prompts and their corresponding function values, and the kernel function. We used an expected improvement acquisition function, A, to measure the potential improvement of a new candidate soft prompt over the best soft prompt we found so far. This function calculates the expected increase in the function value h, p, over the highest function value found so far, under the assumption that h, p, is a random variable whose distribution is defined by our current understanding of the function h. The next soft prompt to be explored is determined by finding the one that maximizes this acquisition function. We converted this soft prompt into an instruction using an open-source language model. We then tested the effectiveness of this new instruction on the black box language model in terms of its zero-shot performance. This Bayesian optimization procedure repeats, continually adding new soft prompts and their corresponding function values to our training data, until we find a soft prompt that gives us a maximum function value h, p, that doesn't significantly improve with further iterations. This overall process is illustrated in the InstructZero pipeline. Section summary. The authors use Bayesian optimization to estimate the black box objective h, p, and find its maximum. They apply a Gaussian process, GP, as the prior for the black box objective h, p, and use the expected improvement acquisition function, A, to determine the next soft prompt to explore. The new soft prompt is converted to an instruction and applied to the black box LLM for evaluating its zero-shot performance on the target task. The procedure is repeated until convergence. Section 3.2 Instruction-coupled kernel. Our discussion now shifts to the topic of instruction-coupled kernel, a key element of the Bayesian optimization (BO) process. The type of kernel we choose in BO plays a significant role as it directly influences the mean and variance of the posterior, which in turn guides the entire optimization process. In our model, InstructZero, the goal is to optimize instructions in the instruction space, although we carry out BO in the latent space of soft prompts. The selected kernel in the latent space must therefore reflect the similarity between the instructions generated for the target task. In other words, the kernel used in the latent space should be aligned with the similarity of instructions. For this purpose, we've created a unique instruction-coupled kernel. In this context, we assume that the BO process has already explored M soft prompts up to this point. These prompts are converted into M instructions using the open-source language model, LLM. To establish a connection between two soft prompts in the latent space, we select a kernel function, L. Common choices for this function include Mattern or squared exponential kernels. Applying this kernel function to the soft prompts results in a kernel matrix, L. We also need a way to measure the similarity between two instructions for the target task. For this, we define another kernel function, S, which could be based on their zero-shot predictions on the target task data. Application of this kernel function to the instructions gives us another kernel matrix, S. Next, we propose a unique instruction-coupled kernel function that merges the two kernels, L and S. This function is designed such that, when applied to the soft prompts, the resulting kernel matrix K exactly recovers the instruction matrix S. Essentially, this proposed kernel maintains the similarity of instructions in the soft prompt space. Moreover, for any new soft prompts that weren't part of the initial soft prompts, our instruction-coupled kernel operates as a smooth extrapolation kernel. By combining the kernels of these two spaces, our proposed kernel aligns both in the latent space of soft prompts with the instruction optimization in the structured space. A visual illustration of this process can be found in Figure 1, which demonstrates when the kernel matrices are computed in the Bo pipeline of InstructZero. Section Summary. The choice of kernel in black box optimization is crucial as it guides the whole optimization process. In InstructZero, a novel instruction-coupled kernel is proposed to align the latent space kernel with the instruction similarity. This kernel combines two kernels, one to measure the correlation between two soft prompts in the latent space and the other to measure the similarity between two instructions in the target task. Section 4 Experiments. Section 4 Experiments. This part of our study is aimed at assessing the effectiveness of our tool, InstructZero, in identifying instructions that guide a black box large language model, LLM, towards a desired outcome for a particular task. Our extensive tests show that our approach can create instructions that not only boost task performance but also produce results that are as good as or even better than those generated by previous methods. Interestingly, InstructZero sometimes comes up with valuable strategies for optimal prompting, which can then be applied to new tasks. Section 4.1 Tasks, Datasets, Baselines, and Implementation. Regarding the tasks, we have put to test the zero-shot in context learning on a series of instruction tasks previously proposed, covering all 24 tasks used in earlier auto-instruction research. To ensure a more comprehensive assessment of all methods, we've added an additional 8 tasks, bringing different aspects of language understanding into play. We've included a full description of each task in the appendix. We use training set examples for optimizing the instructions, but the final instruction, denoted as P*, was tested on a separate, held-out test set. The performance of this zero-shot method, marked as H*P*, on this test set is reported in our results. Section Summary. The authors evaluated InstructZero as a tool to improve task performance by generating instructions that steer a black box LLM towards a desired downstream behavior on a target task. Their experiments showed that InstructZero could effectively generate instructions that enhance task performance while achieving predictions on par with or even superior to those created by previous methods. Additionally, InstructZero produces instructions that sometimes reveal valuable tricks for optimal prompting that could be subsequently applied to new tasks. Section Baselines. We put InstructZero to the test by comparing it with two other methods. The first one, APE, makes use of a more advanced large language model, LLM. In fact, we even upgraded the original APE's LLM to ChatGPT for a fairer comparison. The second method is called Uniform, which conducts pure exploration. It utilizes the same models as InstructZero and it generates an equal number of soft prompts. The distinction here is that Uniform doesn't involve an iterative Bayesian optimization (BO) process. Instead, it relies on uniform sampling. To assess these methods, we use a simple binary loss as our scoring system. In our experiments, we designate this as H. The essence of it is quite simple. If the output from our function, which takes the instruction and input, matches the target answer, we award a score of 1. If not, the score is 0. To obtain an overall score, we calculate the average accuracy of executing these instructions across all validation examples. But there's potential for a more nuanced scoring system too. For example, we could use the log likelihood of the correct answer given a certain instruction and input. It's important to note that the scoring function we use largely depends on the kind of outputs the underlying LLM gives us. For instance, GPT-3 provides the log probabilities of the most likely tokens, while ChatGPT only provides the generated answer. As we're using ChatGPT as our black box LLM in these experiments, our scoring function represents the execution accuracy. Section Summary. The paper compares InstructZero with two baseline methods, APE and Uniform, using a simple 0 to 1 loss as the score function. The score function computes execution accuracy by averaging over all validation examples, and a more fine-grained score can be the log likelihood of the ground truth answer under instruction V and input X. The choice of score function depends on the outputs provided by the black box LLM, and in this case, ChatGPT is used as the black box LLM. Section Implementation Details. We've constructed InstructZero based on the model presented in Figure 1, using Vicuña and ChatGPT as the open-source language learning model, LLM, and application programming interface, API, LLM, respectively. For each task, we select 5 samples as the examples and another 20 as the validation set. We experiment with different quantities of tokens in soft prompts, testing with 3, 5, and 10 tokens to find the optimal number based on the performance with the validation set. We create a random projection matrix A, where each entry is a number randomly chosen from a range between -1 and 1. The dimension of the vector P, which represents soft prompts, is fixed at 10. In our experiments, we use a version of InstructZero that operates in mini batches, examining 25 soft prompts in each cycle. We introduce a notable change. We now choose the top 25 soft prompts with the highest values of U, corresponding to each prompt, instead of simply seeking the maximum of equation, referenced in line 8 of the algorithm. We employ an evolutionary search algorithm known as Covariance Matrix Adaptation Evolution Strategy, CMAS, to pinpoint the most effective soft prompts. All of the training and tests are carried out on a single NVIDIA RTX A6000 GPU card. Moving on to our main findings. The zero-shot test accuracy of ChatGPT was evaluated with instructions generated by APE, Automated Planning and Execution, Uniform, and InstructZero for a total of 32 tasks. InstructZero showed comparable performance to APE on straightforward tasks like letters list and sum, where APE already displayed perfect execution accuracy. However, InstructZero clearly outperformed on more complex tasks, like unscrambling and taxonomy animal, where APE encountered difficulties. When we exclude simpler tasks, where both the baseline and InstructZero achieve 100% test accuracy, it's clear that InstructZero's instructions outshine those produced by the other two methods, and by quite a large margin. We've documented the best instruction formulated by InstructZero for each task in the appendix. A continuous improvement in zero-shot accuracy of the top 15% of instructions was observed across multiple iterations of InstructZero. This points to an effective optimization process. However, in simpler tasks like sum, the optimal instruction was found in the very first iteration, rendering further optimization unnecessary. Section summary. The authors implemented InstructZero using Vicuña and ChatGPT as the open-source LLM and API LLM, respectively. They drew tau equals 5 and 20 samples from the training set as the exemplars and validation set D_T, respectively, and searched for the best value among 3, 5, 10 for the number of tokens in soft prompts. They utilized an evolutionary search algorithm CMAS as the optimizer to find the top soft prompts and demonstrated that instructions generated by InstructZero significantly outperform those produced by the other two baselines by a large margin. Section 4.3 Ablation Study. In Section 4.3, we conduct an ablation study to validate the effectiveness of our optimization strategy in InstructZero. We evaluate it against two other methods. The first is the manual method, where we replace the InstructZero optimize prompt, symbolized as bold P*, with a meta prompt created by humans. This human-generated prompt is commonly used in automatic prompt engineering, APE, for creating instructions. However, we maintain all the remaining elements identical when testing InstructZero. The second method, without manual, or with O manual, involves removing any prompts altogether. Here, we use only the kappa exemplars, or model examples, as input for generating the instruction, V. We present the results of this comparison in Table X. The table reveals a substantial improvement when we employ the soft prompt optimized by InstructZero, as opposed to the two alternative methods. A striking example is the task named letters list. In this task, InstructZero achieves 100% accuracy, whereas the manual prompt method scores 0%. This significant improvement underscores the vital role the optimized soft prompt plays in generating superior instructions for improved zero-shot performance on various downstream tasks. Furthermore, it shows that Bayesian optimization, BO, in InstructZero is highly effective in identifying the optimal soft prompt. Section summary. The effectiveness of optimization in InstructZero was verified by comparing it against two alternatives. 1. Manual, where a meta prompt, handcrafted by humans, was used for instruction generation, and 2. With O manual, where any prompt was removed and only the kappa exemplars were used as. The results showed a significant improvement when using the soft prompt optimized by InstructZero, indicating that the optimized soft prompt plays a substantial role in instruction generation for better zero-shot performance on downstream tasks, and BO in InstructZero is effective in finding the optimal. Section 4.4 Case Study. In Section 4.4, we carry out a case study, where we visualize the soft prompts that InstructZero investigated over 3 iterations of Bayesian optimization, BO. This visualization allows us to understand how the score of the top-performing soft prompt improves progressively. It also illuminates how BO in the latent space strikes a balance between exploring new possibilities and exploiting known beneficial strategies. To the right of the figure, we present the instructions generated by the best soft prompt from each iteration. We notice an incremental enhancement in the quality of these instructions with each iteration, marked by increased clarity, more specific details, and improved relevance to the tasks at hand. In subsequent figures, we compare the instructions created by 3 different methods: Uniform, APE, and InstructZero, all for the same tasks. Both Uniform and APE can generate acceptable instructions, but they often stray from the actual task description. For example, APE's top instruction for one task was to sort the inputs alphabetically and then output the first, third, fifth, and seventh elements of the sorted list. However, this instruction lacks precision. On the other hand, InstructZero produces a more focused instruction, like, find a list of the animals from the input list, which is more straightforward and precise. Similarly, for a formality task, InstructZero demonstrates superior comprehension of the exemplars, leading to more accurate instructions compared to the other methods. Section Summary. The section presents a case study of InstructZero's exploration of soft prompts over 3 BO iterations. The study shows the improvement of the best soft prompt score over time and the efficient exploration conducted by the latent space BO. The generated instructions using the best soft prompt in each iteration show a progressive improvement in terms of clarity, details, and task relevance, outperforming the uniform and APE methods in precision and comprehension. Section 5. Related work. In this section, we're discussing related work that has shaped our study. 1. Large language models, LLMs. The scaling up of transformer-based LLMs has continually enhanced performance in many natural language processing (NLP) tasks. This scale-up has unveiled several capabilities of LLMs, including in-context learning with a few examples, sequential reasoning without prior training or with a few examples, and automatic generation of instructions. In this study, we focus on harnessing these capabilities to generate and refine instructions for Application Programming Interface (API) LLMs. Our experiment, InstructZero, demonstrates that a much smaller open-source model, Vicuña, can optimize instructions to outperform a larger LLM like ChatGPT used in APE. 2. Instruction following and instruction fine-tuning. LLMs can follow instructions, a capacity that can be boosted by instruction tuning. For example, we can fine-tune the model by using human-annotated prompts and feedback on a wide range of tasks, or supervise the fine-tuning process using public benchmarks and datasets. ChatGPT is recognized for following instructions, however, it operates like a black box. Vicuña, on the other hand, fine-tunes the open-source llama using only 700K examples of instruction following from user-shared ChatGPT data, demonstrating similar capabilities to ChatGPT. 3. Zero-shot learning. In situations where fine-tuning the LLM or training an adapter is not possible, such as with black box LLMs, we can optimize the instruction to improve task performance. This is precisely what InstructZero does, offering a challenge complementary to instruction fine-tuning. 4. Prompting and auto-prompt. Prompting uses soft token embeddings, textual instruction, or input-output exemplars of a target task to guide LLMs. Soft prompts can be optimized through backpropagation, but API LLMs only allow hard prompts in natural languages. Optimizing these is challenging due to the complexity and structure of the search space. InstructZero optimizes instructions without using reinforcement learning by applying Bayesian optimization of a soft prompt. 5. Bayesian optimization, BO, has become an effective method for black box optimization across different fields over the past decade. Given that we're aiming to optimize instructions for a black box LLM, it's akin to using BO in highly structured spaces, which can be challenging. Recent approaches aim to solve this by reducing the combinatorial black box optimization to BO in a latent space, using mappings learned by deep generative models, DGMs. Our instruction-coupled kernel attempts to align the soft prompt kernel with the similarity between instructions. This kernel has a unique form and aims to guide the open-source LLM to explore different soft prompts and generate superior instructions. Section Summary. The scaling up of transformer-based language models has led to numerous capabilities, including few-shot and context learning, zero-shot, few-shot sequential reasoning, and automatic generation of instructions. InstructZero uses Bayesian optimization to optimize instructions for black box LLMs without the need for predefined triggers, while also leveraging open-source models to generate instructions. The instruction-coupled kernel aims to guide the open-source LLM to explore different soft prompts and generate better instructions.